I'm going to be walking you through our How to Choose document that's intended to provide some additional information about how to use the 2018 sea level rise projections that were developed as part of the Washington Coastal Resilience Project. And it's great to see so much interest in this topic, and we hope that we will be able to give you a good sense of how to use these numbers with this document. Just a moment here waiting for my slides to catch up. Great, there we go. And so I'm going to start by giving a brief summary of the 2018 projections and how they differ from sea level rise projections that we've had for this region in the past. These 2018 projections include the latest information on sea level rise research. Go back here one slide. Have to bear with me, there's a bit of a delay in advancing the slides. Well, maybe I'll skip through that slide. So the key differences in the 2018 projections are that they are based on the latest sea level rise science. They are local in that they include vertical land movement along Washington's coast. So this gives the variation in the projections at the local scale based on areas of the coast that are uplifting or subsiding. And the third key difference is that these sea level rise projections are probabilistic. That means we have associated probabilities with each of the values within the range of the projections. So this is significant new information included in these projections. And with that comes a need to make some very conscious decisions about which numbers are used and how to choose those numbers for different situations. So the How to Choose document includes 4 different decision points, and I'm going to walk through the processes of making these decisions. The location that you use, which time frame you use, which probabilities of sea level rise you select, and for which greenhouse gas scenarios. And one of the key points that I want to make here is that science has given us these sea level rise projections. They were developed as part of the Washington Coastal Resilience Project. And the science is really in the numbers and the range of projections that are given. But in terms of which numbers you choose to use from that range is not a scientific question. Science can't answer that. It's really a question about your organization, the risk tolerance of your organization, and what is appropriate for a given situation. And so what we are intending to do with this document is guide you to the right questions to ask when deciding which numbers are right to use for your application. The document is also organized around 4 different potential uses of the sea level rise values. And these are certainly not exhaustive. There could be other uses as well, but these are common ones that we've come across in helping people to use these numbers over the last couple years. So some people are interested in using them for vulnerability assessments and resilience plans or risk assessments. Other people may use them in planning, such as comprehensive plans or plans for the Shoreline Master Program. They can be used in very specific project design, such as design of infrastructure, or in nearshore restoration projects as well. And the decisions that need to be made in terms of choosing which numbers to use are similar for all these applications, but there's different factors that you might consider depending on which use you are interested in or working on. We also want to acknowledge that potentially all these uses may be going on in one organization at the same time. And I also want to just briefly talk about what you do with the numbers once you select them before I jump into each of the decisions. So these sea level rise values are the expected change in average sea level. This is change relative to the 1991 to 2009 mean. And they can be used to evaluate the future change in any current water level. So a common use of them is to apply these change values to the current mean higher high water value. And that gives you what would be the future mean higher high water with sea level rise. It doesn't have to be mean higher high water. There may be cases where mean lower low water is more of interest, particularly looking at lower intertidal habitats or navigation applications. So really they're flexible in their use in that they're not tied to any specific current water level. The other thing I want to do throughout this presentation is to point you to the other documents as part of the Washington Coastal Resilience Project, because they can provide additional information on any of these topics if you'd like to follow up with more detail. So what I'm describing here is described in more detail in the guidelines for mapping sea level rise and inundation. And to show you what this looks like in a coastal profile, so here would be our current water levels. We have mean sea level. Below that, you have the mean lower low water and the mean higher high water. So that is the daily average high tide for a particular location under current conditions. And then if you're interested in that future mean higher high water, you can simply take the sea level rise values that you choose. In this case, we're looking at 2 feet, and add that to the mean higher high water. And now you have your new future higher high water. We also recognize that many people are interested in water levels that are more extreme than the mean higher high water. So higher water levels that occur less frequently due to storm surge or waves. And these values can be used in combination with that information as well. So there is another document in our series, Extreme Coastal Water Levels in Washington State, which provides some information on what these more extreme coastal water levels are around the state and how to combine the sea level rise information with that. So an important consideration when using these is what water level are you concerned about for your application? So are you interested in that daily average high tide? So the area that would be inundated on average once a day, or are you interested in something that is less frequent but a higher water level, such as a 10-year coastal flood or the FEMA 100-year flood level? And just as we did with mean higher high water, you can add these sea level rise projections to those more extreme water levels. For example, the current FEMA 100-year base flood includes the storm surge and waves in most area. And by adding sea level rise to that, you're getting what that 100-year flood would be in the future. The current modeling of the 100-year flood does not include any sea level rise information. So now I want to walk you through the decisions that need to be made when selecting numbers, and these follow the decisions that are included in our document. So as I said, the projections are local. There's 171 segments along Washington's coast. The size of those segments varies just because of the irregular coastline. And the projections of sea level rise themselves differ among the segments simply because of that vertical land movement. So in places where you have subsidence, there will be a higher rate of sea level rise. In places where there's uplift, there'll be lower rates of sea level rise. And there's a few options for selecting locations depending on your application. If you are looking at project design or a nearshore restoration project in a specific site, you can simply select that single location and use those values. There may be situations where a planning or a policy situation where you want to be looking at the projections for a larger area, such as the coast of an island or a county. In that case, you have a couple of options. You can select a representative location, and a Tableau visualization tool that we have for viewing the data will allow you to look at different projections in your area and identify what a representative location would be. You also have the option of looking at multiple and averaging multiple projections for your area of interest, and you can download the data from the Tableau visualization tool and simply average the values for multiple locations. One comment, though, that I want to make about that is that these projections are intended to be local by picking up that fine scale variation in vertical land movement along the coast. And so in areas along the coast, such as the ones that I've circled here, there's a very steep gradient, a lot of variation in that vertical land movement over a short area. And so in these cases, it would not make sense to average multiple points along the coast, because that would result in values that aren't necessarily meaningful and average out that local variation. The next decision that needs to be made is about the time frame. So unlike previous projections that typically gave a value for simply 2050 or 2100, the 2018 sea level rise projections provide values for every decade between 2010 and 2150. These decades are actually the average of a 19-year period centered on the decade. So for example, 2070 would be the average sea level rise for 2061 to 2079. And when you download the data from the website, you can see all these decades and select whichever one is most appropriate for your application. So this increases the flexibility of the data and allows you to really select a time frame that's specific to how you want to use the information. There's a couple of different things to consider when you're trying to decide on a time frame, and this really varies by your application. If you're looking at vulnerability or risk assessments, it makes most sense to select multiple time frames and compare how the risk associated with sea level rise would change over time as part of that assessment process. If you're using an application of policies and plans, then you can take into consideration the time frame of that plan. Is it intended for 20 years, 50 years? But also consider what that plan affects. If it affects coastal development, are you looking at coastal development that may actually last much longer into the future besides the time frame of the plan itself, in which case you would want to look at a longer time frame. Another important consideration is potential updates and revisions. How often can your plan be revised or updated? If it's a fairly frequent revision schedule, then using more near-term timeframes may be appropriate. If it's difficult to revise a plan or update it in the future, then you might want to consider longer timeframes. Project design is probably the most straightforward situation in selecting a time frame. In this case, often infrastructure has a designated design life, and that can be a good indicator of the time frame you would want to use. So for example, if you're building a road with an 80-year life expectancy, then selecting projections for 2100 would be appropriate. One of the things that we have come across in this process is that learning that the specified design lives of infrastructure often differ from the actual design life, where in some cases you may have infrastructure that is upgraded more frequently because of technology and therefore has a shorter design life in reality, and you could use more near-term projections for that. Whereas we also hear the opposite is often true, where infrastructure is maintained to last much longer than its design life just because of funding and the ability to upgrade. And so in that case, you might want to be thinking about an even longer time frame. And for nearshore restoration projects, there can be a variety of different goals, and different timeframes would be relevant. There can be near-term, short-term habitat goals, and short-term projections would be appropriate for that. On the other hand, if the focus is really restoring ecological processes for the long term, then long-term projections 2100, 2150 may be more appropriate. And we've also heard that for restoration projects that are focused on processes, the rate of sea level rise can be particularly important. And the rate is not included in the values directly, but it can be easily calculated from the data if you want to look at the rate of sea level rise relative to other processes like marsh accretion. And the third decision is about probabilities. So these projections include a full range of probabilities from 99% to 0.1%. At the high end of the probabilities, 99% to 83%, these are low values of sea level rise. And these values are very likely to be exceeded in the future. On the other end of that range, we have the 17% to 1%, which are very low probabilities, high values of sea level rise, and these are less likely to be exceeded. In the middle of that range, we have what we call the likely range, which we have designated as the 83 to 17% probability. And in the very middle, of course, is the 50%, which is the most likely value. So with 50%, that means that sea level rise is just as likely to be above that value as not. So for example, in this graph here, you see that the 50% value in 2100 is 2 feet. So that means sea level rise in 2100 is just as likely to be above 2 feet as below. And at the very low end of the probabilities, we have the 0.1% probability. This is an extreme low probability that's intended to be a physical upper bound to what sea level rise projections could be in the future. And the idea with this is simply that even with additional research on sea level rise, this upper bound is unlikely to be revised in the future. And the intention of these probabilities is that they can relate very directly to risk management and thinking about managing your risk for sea level rise. So if we go again to those high probability values, the low amounts of sea level rise, these are really most appropriate to risk tolerant situations. So applications in which your project can tolerate sea level rise being greater than the values for which you plan, because these are likely to be exceeded. On the other end, the 17 to 1% probability, these are for risk-averse situations, so applications that really cannot tolerate sea level rise being greater than the values that you plan for, and this is a fairly conservative part of the range to use. So for example, this might be in the application of a wastewater treatment plant. On the other end, on the risk tolerant side, appropriate applications for that might be things like a parking lot, a picnic area, a campground, or infrastructure that can tolerate some sea level rise. And then in the middle again, with moderate risk, is the 17 to 83% probability. And so our fourth and final decision is about the greenhouse gas scenario. So that probability range that I described is available for each of 2 greenhouse gas scenarios. So these greenhouse gas scenarios are essentially different futures associated with climate change based on different assumptions about population growth and emissions. The key information to know for this is that the RCP 8.5 greenhouse gas scenario is for more warming and therefore a higher rate of sea level rise that reaches a higher value by 2150, compared to RCP 4.5, which is a lower greenhouse gas scenario and therefore has lower warming and a lower rate of sea level rise through the century. One of the critical things, as you can see from this graph, is that the sea level rise projections for these 2 greenhouse gas scenarios do not differ until about 2050. So if you're using a time frame and selecting numbers for your application prior to 2050, it doesn't necessarily matter which greenhouse gas scenario you choose because they're essentially the same. If you're looking at timeframes beyond 2150, then it's important to consider which of these greenhouse gas scenarios you would like to use. Some considerations for that, for example, again, for vulnerability assessments or risk assessments, the most appropriate thing is probably to compare both greenhouse gas scenarios and sea level rise values for those to see what the different impacts may be and determine to what extent it makes a difference depending on which one you use. Another important consideration, particularly in policy and planning, is consistency with climate change information that may be used throughout your organization elsewhere. So these greenhouse gas scenarios are not only used in a sea level rise context, they're used for other climate change projections that may relate to terrestrial systems or water resources. And so one of the things you may want to consider there is consistency throughout your organization as to what other greenhouse gas scenarios are used. And so, I just want to say again as a reminder that these decisions are really institutional decisions that are based on your institution's risk tolerance and what may be appropriate for the context in which you're using the values. And that really requires some internal discussions within an organization in terms of making those decisions. And so I just want to close by saying that the choosing values to use for your sea level rise application is really actually probably the first step in the process. There certainly needs to be some outreach and engagement around those values. We've heard that in many cases where people are applying these, that the public it may be appropriate to give the public an opportunity to weigh in on which values you're using and why. And then of course, the most important next step is, what do you do differently based on those sea level rise values that you've selected? So for example, if you're using them in a project design application, how is that project going to be designed differently? How would you design a nearshore restoration project differently based on the sea level rise values that you've choose? And these projections were updated in 2018, as I said, and we know that the science around sea level rise is evolving, and likely new science will change the projections in the future. Given that we have this wide range, we wouldn't necessarily expect the range of projections to change, but the probabilities associated with values within that range may change. And so part of your process in using these values is to think about how you might revisit them in the future and build that flexibility and opportunities for updates within your applications for the information. And that is what I have, and I believe at this point I can take some questions.